So Ivan already mentioned, of course, one of the very big topics that we had for the 2.4 release was Intel's decision to discontinue Optane persistent memory. And of course, Deos has been heavily relying on storage class memory that is byte addressable, right, for the versioning object store. That is the key data structure in Deos. What I want to do in the next 15 to 20 minutes is to walk you through an overview of this technology. There is a paper that we did in association with the IXBug at ISC23. So for those of you who attended the ISC23 session, apologies. Most of that will be a repetition. The paper out there is actually not publicly available. It's behind a paywall. Please just send us a note if you're interested, and we can certainly share it. So we had to redraw the overall high-level architecture picture of Deos. Right? In the bottom, you see the server side, where up until the 2.2 release, storage class memory meant PMEM. Right? That's the blue DIMMs on the left-hand side, where you create a file system, essentially an ext file system that you mount with the DAX attribute, which means you're not going to the Linux page cache. You memory map that, and then we can do load store operations into the persistent memory. That was the old model, which of course is still fully supported. And we actually have some new team members in our team that are part of the original PMDK team. So we also have all the skills in the team to keep supporting PMEM for the lifetime of the systems that customers are running with PMEM. So that's not going away. But with the cancellation of the Optane 300, which was originally planned for Sapphire, we had to come up with an alternate code path, and that's what I'm trying to show in the picture here. So for the storage class memory piece, starting with 2.4, you can have all the versioning object store in DRAM, which of course is volatile, and in order to protect that, there are two things that are happening that I'll showing on the next slide. The most critical one is that we have to do a write-ahead log to SSD, just to make sure we keep consistency in the case something happens to DRAM. And then you have the bulk storage, which, as before, is accessed through SPDK. So that's the usual like block IO level access to the bulk data that we had previously, which is done through the SPDK interface. So if we look at this in a little more detail, this is the PMEM version of the code path, where in blue you have persistent memory. Every target on the engine has its own section in this persistent memory area where it holds the versioning object store. All the modifications to the data are essentially tracked in those VOS data structures, and all the actual user data that's smaller than 4 kilobyte is also stored in PMEM. That's the small green blob on the right-hand side here. So with the availability of future CXL devices, we may get at some point persistent CXL, and we may have more hardware choices then to also use this model of physically persistent data. But today, with the end of Optane, essentially that path has no immediate future. But there is a workshop here also talking about new memory technologies. There's a team from Israel that has already prototyped CXL.mem persistent devices. This is like FPGA basic setups, right? But there are teams working on this, and of course all the storage vendors are also very active on the CXL side. So we believe that there will be future CXL technologies that we can also pick up at a later point in time. But for now, this is the new model where we are using DRAM for the VOS tree. So instead of a PMEM that is mapped into the file system with DAX, now it's just a TempFS file system. So if you create a Deos server with this, what we call metadata on SSD code path, and I'll show you in the next slides how to do that in the configuration, then the VOS tree will be in DRAM, which means it's faster, right? But it's also more expensive in terms of the capacity than what you would get with PMEM. And then to make that persistent, two things happen. In the data path, in the critical path, if you will, we are doing this write-ahead log. So performance of that logging will directly impact the data rates and metadata rates that we can get from an application, right? And then in order to make this more efficient, there is also an asynchronous checkpointing of essentially the whole VOS data structure, not just the immediate modifications, but the whole state of the system. This is not in the critical path. This is done asynchronously, and there are multiple ways how you can trigger that. You can trigger that time-based, or you can trigger it based on like memory pressure in the system. And that's also something where we still have to experiment a little bit in which workload environments does it make sense to just go with like a time-based asynchronous checkpoint mechanism versus areas where maybe you don't have enough DRAM in the system and you run into those phase pressures more often. Those are configurable settings that you can set when you configure the server, essentially. So all of that stuff goes to NVMe disks. So at the bottom, you actually see 3 different types of NVMe usage now. On the right-hand side is the traditional data, right? Everything bigger than 4 kilobytes. And on the left-hand side, there is this small wall blob, which can really be, the size is not very big. And you have the meta blob, and the phase 1 implementation that Ivan mentioned essentially means that the green checkpoint of the VOS data structures cannot be bigger than the blue VOS data structures in memory, or turned the other way around, your memory has to be big enough to hold all of the metadata. In phase 2, we will do what's already in this picture here, where the VOS tree in the green SSD checkpoint is actually bigger than what you have in metadata, in memory. That's not available today in the 2.4 release. That will come later in the phase 2. But that is commercially critical, right? Because we don't want people to put like 2 terabytes of DRAM into their servers. So the idea here is that we can distinguish like hot and cold metadata. We can migrate off parts of the versioning object store tree onto SSD and only bring it back when it's actually needed. And that way we can reduce the memory consumption on the storage engine side to a level that is like cheaper to build a Deos server. So that's the caveat working with the phase 1, right? You really have to size your memory accordingly, and that can get very expensive. On the other hand, if you're doing like early evaluations, or you don't have like hundreds of millions of files immediately from day 1, you can definitely start with a like a DRAM-only version and size the DRAM capacity a little smaller than what you would do with persistent memory. If you're thinking about creating those systems, get in touch with us. We definitely have some sizing guidelines for this phase 1 environment, and we can look at the expected workloads in terms of like number of files and file sizes. So the good thing about this from an end user perspective is there's really not much change. There's no change on the client, and there are very isolated changes that we have on the server software side. So the only thing that changes is essentially in this unified memory allocation mechanism. There is now essentially a callback that will allocate space for the write-ahead log that now goes to SPDK whenever those logging entries are written from the storage class memory side. So it was possible to implement this in a relatively quick time. Most of the areas where right now we say it is a technology preview and not completely production ready is in failure scenarios, right? When you have faults on the drive side, for example, making sure that we really validate all the things that can go wrong before we bless this for general production use. So this is kind of an eye chart, but one of the most important things from a solution design perspective now is how do the servers look like where we put these things in, and what do the physical capabilities of the server mean for the possibilities, for example, of number of SSDs that you can put into a server. So these are like Sapphire Rapids 4th generation Xeons. It's a system where each socket has 80 PCI lanes. And what I show here is 3 different versions how you can configure this. On the very left, this is like a capacity configuration for Deos, where you have 1 engine per socket as before. Every engine has 1 network interface, which in this time frame can be 400 gigabit NDR. Right? And then the rest of the PCI lanes, minus a few for management Ethernet and stuff like that, can be used for NVMe SSDs. So in terms of the quantity of drives per engine, you can put, I wrote 4 to 14. The lower bound 4 is because you need at least 4 drives to saturate the network link If you don't have 4 drives, you've just wasted money on the network side, right? And then depending if you size for read-oriented or write-oriented workloads, you can increase the number of drives up to 14 per socket. After that, you run out of PCI lanes. So that's the boundary for the traditional sizing that we also had for all the previous releases, right? And the middle shows the same thing essentially with a new feature that we have where you can run more than one engine on a socket, on a CPU socket. And the goal for that was if you don't have 400 gigabit yet, you can put a 2-port 200 gigabit adapter in the same 16 PCI lanes with Gen 5, right? And you get the same overall per server bandwidth, but you're only using an HDR network, for example, right? So that feature was introduced also with 2.4. We had instructions to do that manually before that. So we eventually run 2 engines per socket. Each engine controls its own network port as before, and each engine controls half of the SSDs that are connected to that. And in terms of quantities, this is then like 2 to 7 Gen 5 NVMEs to saturate such a configuration. And then on the very right-hand side, this is now exploiting the fact that Sapphire Rapids has more PCI lanes. We can actually now plug 4 16-lane 400 gig ports into a dual socket server. Right? And that leaves PCI lanes to connect either 4 or 5 NVMe disks. So this would be the highest possible performance 2-socket server, right? And the choice is really 4 or 5 disks. And that's what I will focus on in the next few slides here to show you what the configuration looks like, whether you want to run with like a PMEM configuration or an MD on SSD configuration. So sites who are using Deos as a dedicated extreme performance tier will go to the right-hand side and run 4 interfaces per server, right? If you want to have more like a capacity-oriented setup with still like up to 90 gigabytes per second, you can put more SSDs per engine, so the cost per capacity goes down, but you get a lower overall performance, of course. So here I'm showing an excerpt from this Deos server YAML configuration file from the old world, where on the left-hand side, you specify the first storage class as DCPM. This is an acronym for the old Intel marketing term, DC persistent memory for the PMEM, with its mount point, right? And you specify a class NVMe where you put all your data disks. That's what a production server like at Argonne or LRZ looks like right now. People have been using the Deos implementation with just ephemeral storage, so they just put DRAM, RAM as the storage class memory specifier, right? In this case, if you do it like this, you will lose your file system when you lose your boot your server, for example, or anything happens to the DRAM. So this was really for ephemeral scratch usage, but some people have actually used this quite heavily. The NVMe class looks exactly the same. It's just a list of drives. So that's the state of the code path before metadata on SSD. If you want to use metadata on SSD, you have to change that configuration. And the main thing that you have to do is on the NVMe class, if you look at the left-hand side here first, you now have 3 BDEF roles. And those correspond to the 3 different green boxes that I showed on the high-level architecture. There is the data role, which is what Deos used to do before on the NVMe disks. There is a meta role, which is used for the asynchronous checkpointing of the VOS data structures. And then there's the WAL role for the write-ahead log. And the question that you have to answer when you design a system is, which SSD do you use for which purpose? That depends heavily on the type of SSD that you're using, because different models have different performance characteristics, and the quantity of drives that you have. In this case here, on the left-hand side, we are sharing all the drives that we have, all the 4, which is not much, right? We're sharing all 3 roles on those drives. So there is no dedicated SSD for the write-ahead log. Everything goes to the same physical media. And it's by default like striped across all of them. There may be reasons when you want to dedicate, for example, 1 or 2 faster SSDs to the write-ahead log. And that is shown in the middle, where essentially now you have 2 different NVMe classes. One has the role WAL and the other one has the role meta and data. And on the right-hand side, there's a third option that you can choose where you put both the asynchronous checkpoints and the write-ahead log onto dedicated disks, and you use the remaining disks for the data just as before. That configuration is mostly attractive for the case where the data disks don't have good endurance, right? And you expect that you do a lot of checkpointing, then you want higher quality drives to be used both for the write-ahead log and the checkpoints. We have done some measurements, and there's more details in the paper than I mentioned, going through the standard like MD test metadata tests. But at this point, we've only done that with a homogeneous population of disks, which are the Intel or now Solidigm P5500s. We are right now setting up some more experiments in our lab with dedicated drives for the metadata to see if that makes a difference. But what I'm showing here is a simple example where we run one storage engine on an HDR InfiniBand fabric. We have configured a storage pool of 8 terabytes, and we're running a standard like IO500 type MD test with a stonewall time of 30 seconds. And what I show you is a 0-byte MD test ERI cases, but on the paper we also have the MD test hard, where the data is so small that it will always fit into the SCM, right? And then we doubled that as well to check the effect of writing the data from the MD test files actually onto the data SSDs. What these charts show on the x-axis is just the number of MPI tasks. So it's the number of client nodes in the configuration times the number of MPI tasks per node. And I apologize, it's a little small to read here, but I'll explain the curves. On the y-axis, it's the MD test IOPS, millions per second, right? And we are looking at 3 different scenarios that you can distinguish from the color of the curves here. So there's always a test with 1 client, and then 1 up to 64 tasks probably. And there's another run with 16 clients also going from 1 MPI process to 64 processes. And that's how we span the total like MPI count, task count from 1 to 1,000, sorry. And then there's 3 sets of tests. The top one, which is the purple curve, that's the traditional PMEM configuration where you're using persistent memory for the VOS tree, right? And we're using all 4 drives for data. That's why the label on the curve says 4D. All 4 SSDs are used for data, and we have the PMEM for the rest. And unsurprisingly, that has the highest performance for the left-hand chart here, which is the MD test easy write, so just file creates. The positive surprise for us was when you switch to this model where you are using the MD on SSD code pass, you're using the same 4 drives, and you share those drives for the write-ahead log, for the checkpoints, and for the data. That's the light blue curve, or the orange one for the lower task counts. It is lower, but it's actually pretty close. It's like 15 to 20% lower in the cases where like the distance between the two is the biggest. And then at the bottom, the yellow curve and the dark blue on the left-hand side, that's where we have actually separated out 1 drive to be dedicated essentially for the write-ahead log. And now we only have 3 drives remaining for the data. And what you see is that for this particular case, when you only have 4 NVMe disks, that's actually a bad choice, right? The performance is lower dedicating 1 drive. It has lower IOPS than 4 drives, and you have less capabilities also on the remaining 3 drives in the data part. So in this case, when you're looking at a performance-oriented system going forward with 4 or 5 drives per engine, those first experiences here with the same drives used for everything definitely say share all the 3 roles. We are redoing this exercise with, for example, the Kioxia FL6 drives, and we'll definitely also talk to our friends in other SSD providers to see if it makes a difference if you have specialized drives for the write-ahead log. Yeah, Phil?
For those of us that aren't super familiar with what exactly MD test does, what operations are happening in the left graph? Is that just a create?
This is just a file create. The MD test easy write is a create of a 0-byte file. So it's all metadata, there's no data. We have the same numbers when you do the MD test hard write, which writes 3,901 byte, which is below the 4 kilobytes, so it stays in the VOS structures. Exactly. And so in the write case, And the case for the MD-Test Easy Delete, which is also 100% metadata, looks exactly the same. PMEM is fast, then or fastest, and then the case where we're using all drives for all purposes is in the middle, and like sacrificing one drive for the write-ahead log makes things slower in this setup. If you have like 14 drives per engine, that picture may change, right? You may have like 10 or 12 drives for data and dedicate a few specialized SSDs for the metadata operations. But we didn't get to that yet, but that's lined up as a test case. We have a bunch of Sapphire servers set up now with, I think, 20 or more drives, so we can look at that design space. On the right-hand side, that's also not a surprise. This is stat. So read-only workload. We don't have to write a write-ahead log because nothing changes, right? So there should be no difference between the different code paths. And actually, you see that the MD on SSD curves, the light blue and the yellow, is slightly ahead of the PMEM, which is fine, right? DRAM is faster. Most of this is software, but you also have to access the data, and reading from DRAM is a little faster than reading from persistent memory. So this is all expected. For the 0-byte case, there's no read, so that's why the left-hand side is empty here. For the delete case, you see the total rates are lower, but qualitatively the curves are looking very similar. We have PMEM at the top with the best performance, because again, if you delete, right, you have to update a lot of data structures, and then we're followed by the shared usage of the 4 drives, and the yellow one is the dedicated single disk for the write-ahead log. So, in summary, what did we do so far and what did we learn? We have this phase 1 implementation, which means that the size of the DRAM memory will limit your total metadata size. And we are very well aware that commercially this is not really viable if you are planning for a huge number of files. We have, initially, I believe, we have set a target of like 6% PRAM capacity versus PMEM capacity versus SSD capacity. We've run quite a few experiments also with like half of that, and for many workloads that seems okay, but even with 3% ratio, when you have to implement this with DRAM, this will get pretty expensive. The good thing is really that the worst case, like 100% empty file create or 100% delete, really doesn't degrade that much. We have expected a much bigger hit, to be honest, on the metadata performance rate. So that's great. And the thing that we still have to learn more collectively and then give advice to you as the people operating those systems is really recommendations on how do you use those different SSDs. Does it pay off to like pay twice the amount of money for SSDs that are specialized for metadata workloads, those types of things. As Ivan mentioned, we did move out the phase 2 from a release perspective because the main focus really was that for 2.6 we want to come out with a quicker release cycle. We don't want that to be delayed by the testing, which is pretty involved for those scenarios. So it's been officially moved to the 2.8 release for a tech preview and then coming out with 3.0 in general. I believe there's also a number of data structure optimizations in the I/O server that go with it, but I'm not the right person to talk about that level of detail because I'm more working on the system level. That's it. Again, if you want to get the paper and you don't have access from your institution, let us know and we're happy to share the document. Right. Any questions?
Michael, can I ask?
Yes.
The metadata, is it entirely replicated across all servers like this?
No, it isn't.
So the DRAM size is not entirely limited on the, in the sense that you can scale up your servers and it doesn't immediately run into trouble.
Yeah, so the question was, is the metadata replicated across the servers? And the answer is no. This is the same design as with PMEM, right? This stuff is local to the engine. If the engine dies, you have to rebuild somewhere else. This is like the SDS philosophy of like no hardware replication or logical replication across systems. That design doesn't change with the DRAM method.
So what size of files, what number of files you get into the very large DRAM, not file objects?
I can't, sorry, I can't get your number here. We've certainly tested like 100 million file type, but it really depends on the capacity of your system. Yeah, let's take that offline. I don't have the answer. Other questions? If not, then I'll